Hello, so my name is Karnbir and I'm just a chill guy. Okay, so this week we're learning cues and yeah, so I'm gonna talk about cues and how they're done, how they're implemented, and I'm also gonna focus on a little bit more about linked list and touch up on specifically doubly linked list, circular linked list, and how they relate to cues. Also for this video, I'm gonna do less teaching and kind of more like exploration. So I'll do a bit more Googling. The video will be longer. If you want to sit along and watch it, go ahead. But as always, I always recommend watching it on 2x speed. Okay, so yeah, let's talk about cues. Let me pull up my iPad. Okay, so a queue is just like a stack. So let me 100% cool. So yeah, a queue is just like a stack. So so queues and stacks are basically essentially the same concept with minor differences. So if you guys remember, a stack is essentially you can kind of picture it like a jar and you pop in elements and then you push out elements. And then the restriction placed in the stack is that you can only pop at the top, peak at the top, and pop out at the top. A queue is essentially the same thing. However, with a stack, you followed something called last in, first out, which stands for, yeah, LIFO, last in, first out. A queue is essentially the same concept. However, instead of doing LIFO, we do FIFO, which stands for first in, first out. So kind of like how you would find a queue of people or a line of people. If you had an open house and you had a line of people, imagine these are all people here, right? Or like let's say it's a restaurant. The person who's first in line will be served first sooner than the other people, and the queue follows the same concept. So first in, first out. So how this essentially works is we're going to treat it very similarly to a stack. So we're going to add in elements, but we don't need the jar analogy anymore. Instead, they're just elements. And the first thing we popped in, which was this, will be the first thing that's popped out. So basically meaning we push in at the head and we pop out at the tail. And we can also do a peak at the head. So that's kind of like what a queue is. We like add in elements, we removed the first element that was added in, and we always push in at the head and we're always queuing up data. Yeah. So where are queues used? I feel like queues would be used for things like scheduling, which is pretty important. So for example, if you have a few customers and they want to deal with your service, you would obviously want to prioritize the person who was waiting the longest, the person who first entered into your queue. So queues are used there. Queues are also used for more technical aspects, such as scheduling of events or things that happen in your computer. So for example, if you have your CPU and you have two programs, and your CPU is busy doing something else, your program will make a request to your CPU and it'll be scheduled to execute at some later time. And then another program can also request from CPU and it'll be scheduled as well. But obviously we want the program that was scheduled in first to execute first rather than the program that was scheduled in second. It also works in the same way for some website stuff. So for like TCP, like there is some queuing that goes on over there and kind of things like that. I'm sure I could think of more examples. Let's try to find some if there are any queue examples in C++. Hopefully there'll be something. I'll open right here. Let's see what AI has to say. So yeah, first in, first out, operating system, printer jobs, breadth first search, which is something we'll learn in 2150, traffic simulation, bank simulation. Yeah. Let's see if Geeks for Geeks has anything else. Web servers. Yeah, so you want to serve the person who is there first. Batch processing, resource allocations, and yeah, kind of like what I mentioned. Yeah, first come, first serve. So anyways, so that's essentially the application of a queue, and I've covered kind of the fundamental concept of a queue, and how I mentioned how queues are just like stacks. Stacks are something called ADTs, which stands for abstract, oh my God, God help me, right? Abstract data type. The type is supposed to be there. Anyways, okay, this is really bad. Is it even readable? I'm not even, I don't even know. Okay, anyways, so yeah, so ADTs, and examples of ADTs are stacks and queues. And something I mentioned about ADTs is an ADT is kind of a data structure on top of a data structure. So just like how stacks, we implemented stacks. So the implementation could occur via an array, which also includes a vector, or it could be implemented via a linked list. And we'll cover a few more different types of linked lists. So an array implementation is pretty unique because array implementation, and also for any implementation, we need to cover the few basic functions. So if you recall from a stack, the functions were to peek, which is to basically read what's on the top of the stack. We had a push to push elements onto a stack, and we had a pop to pop elements off of a stack, right? And then we also had some extra functions that had to deal with the underlying data structure, and those were things such as is empty, and in the case of arrays, um, is full. The is full is not needed for a linked list because for a linked list, we don't really have an is full. Because a linked list, we can grow to whatever size we want. However, an array is fixed size. So that's why we implement the is full only for arrays. But the is empty is universal for both of these implementations. So yeah, so that's what we had for a stack. And let's compare it to what we have for a queue. So a queue implements a peek as well. We can call that front. It implements a push, which we will call in queue. Actually, why don't I use the proper terminology? So we have, let me remove the brackets. So we have an in queue. Yeah, I should probably flip it around. So we have a front, which is also known as a peak. You can kind of call it whatever you want, but I'm just going to follow whatever professor told us. We have an in queue, which does a push. We have a DQ, which is similar like a pop. However, the only difference is we pop from the tail. And we push at the head. And we also peek at the head. And then we have the other functions based on how they're implemented, which is empty. And also in the event of an array, which is fixed size, we have an is full. So as you can see, these are essentially the same thing. It's just that there's one minor alteration, which is that rather than popping off from the head, we're popping off from the tail. That's about it. And because we're popping off from the tail, this jar analogy kind of falls apart. And I don't think it's possible to do recursive like functionality with a queue, which you could do with the stack, because a stack does everything at the top. Let me just actually double check if that's actually the case. Can you achieve recursive, can you do BFS with queues? Sorry, DFS. Uh, okay, so while technically possible, it isn't standard. Okay, so depth first search, which is like the recursive functions that we've been dealing with, where we can essentially traverse the tree, are possible with stack because they naturally align with this last and first out order. But a queue doesn't do that. A queue does first in, first out, and that's naturally more suited for BFS, which I believe we'll cover in 2150, and that's out of scope for this course. Cool. Okay, so quick answer, no recursion-like behavior for queues that we're going to cover in this class. Okay. Okay, so yeah, that's basically what a queue is. I can briefly show you guys the code. I think I have it up, so do I? here. Yeah, so here's some code I made for the queue. So we have our constructor, we have our enqueue, which is like push, we have our dequeue, which is pop, we have a peak or a front, we have a is empty and a is full, and here I used an array, and then simply I would make an array, and it would keep a track of the size and capacity, and I would peek at the head, and I would just do some stuff just to enqueue data. So I'd push, so I would add this data to the wait, oh, it's flipped. So here what I'm doing is I'm adding it to the tail and I'm popping off from the head rather than adding from the head and popping off from the tail. That's essentially all I'm doing. So yeah, so here I'm adding to the tail and I'm keeping track of capacity since we're fixed, and I'm also dequeuing, um, popping off from the head, and I'm moving the head along, and I'm just keeping a track. And yeah, and this is the syntax. We make our queue, we can pop in information, we can dequeue information, we can pop in information again, and then dequeue it, and then everything should be in order. Yeah, so 0, 1. So here I would like dequeue. I forgot what I honestly did here. So yeah, so here the array full comes from here because I'm trying to push in more than 5 elements. And then here, I pop out the first, here I pop out the first 2 elements and I print them out, which is 0 and 1. And then here, I basically dequeue the element, I modify it, I multiply it by 10, and I put it back in, starting from the second. Oh, yeah. So I do this, honestly, like, this is honestly not needed. I could have just done 3, and it would have given me the same result. Yeah. And then here, I just dequeue everything until my array is empty and my program terminates. So yeah, cool. So yeah, that's basically queue. So I did it with an array, and with the array, because it's naturally fixed size. Also, vectors are largely irrelevant. If you really wanted to implement it, you could, but a vector isn't really useful here because an vector is essentially a dynamic array, but it's very slow to add. And a linked list is also like a dynamic array, but with the benefit of being easy to, I mean, not easy, fast to add. So to compare and contrast vector versus linked list, a vector is fast to look up, but slow to add since it has to make since it has to copy the array whenever you would do pushback. A linked list, however, is slower to look up, but fast to add. And I think in the average case, the linked list is generally faster whenever we need to add. If you know that you aren't really going to need to add much and you're going to need to read more, then use a vector. But if you know that you're going to need to add often, just use a linked list. Unless you know that you're only going to add a certain amount, then just use an array. Cool. Yeah, so for arrays, we have to, because array is fixed, you have to keep a track of some parameters. So you have to keep a track of the head. And this is a little bit confusing because we're bringing linked list terminology into an array. But it does help you think about queues in the proper order. So we keep a track of the head and we keep a track of the size. Also, I have to fix my analogy. We actually want to I just want to push to the tail and then pop from the head. Cool. Okay, 1 second. Okay, so we're back and we're going to dive in how arrays are used to implement queues. Okay, let me just go to my iPad. So here I have the code needed to implement a queue. And we're going to use an array, which as you can see is done right here. So for arrays, because they're fixed, we have to keep a track of something called size. But then other than that, everything else is generally the same. There's a head and there's a tail as we would expect from a queue. And just to reiterate, a queue is when we push in new elements onto the tail and they're queued up until they're eventually popped off of the head, which is following this convention of first in, first out. So these queues use an array here, and we have to initialize the size of the array. So our size is fixed, and because our size is fixed, we'll naturally need an isFull method. So here are the typical operands. So we have a dequeue, which functions the same as a pop. We have an enqueue, which functions the same as a push, but however, this is pushing to the tail, and this is popping off from the head. We have a front, which functions as a peek from the head, and we have an empty to check if our queue is empty, and in the case of an array, which has a fixed size, we have an isFull. So to initialize our data structure, we need an internal data structure called the array, and we need to have a few indexes or pointers to keep a track of various positions of the head, of the tail, and of the size. So the E will be responsible for keeping track of a tail. The F is responsible for keeping track of the head, and the N is essentially how much of our queue we filled up. So we can do capacity or size. So keep this in mind. So I don't really like how these variables are named, but just refer to this and it'll help you make sense of it. So our queue, we have a F, an E, and an N, which we are all going to initialize to 0. So our N is our capacity, we have 0 elements full, and our tail and the head are also at the same position. So just to demonstrate, I'm going to start to draw the array and give it a size 1, 2, 3, 4, 5. I know that the size is actually 10, but for demonstration's sake, I'm going to go with 5. And for our empty function, it's quite simple. We simply return what is the current size of the array, and if it is equal to 0, well then our array is empty. And if it is full, we simply determine is the number of elements populated in our array equal to size. And you may be saying that, hey, actually no, this is kind of wrong because the elements of the array is actually 1 less than size equal 5, but something we're going to do is we're going to do n plus plus, which will naturally, once it hits step 4, it will naturally increment to 5, and then 5 will be equal to the size. I may be jumping a little bit ahead there, but just in case you're wondering, that's what's happening here. So that's why we do n is equal to size. Okay, so here are the 3 main functions that we really have to worry about. This is just a peek. This is our push, and this is our pop. So let's go through them together and help you understand what's going on. So first off, whenever we want to push in something, we have to check if there's space within the array. And if there's not space, well, obviously the data is going to be lost or the data is going to go out of bounds, which is bad behavior. So we always want to do that check first, where we call the isFull function. And the isFull function simply checks if the current capacity is equal to the max capacity. Okay, and if it is, we're just going to std out, and here we're doing std sir, which is just like c out, but c stands for error, and it just is useful for printing off error messages, I guess. And then this exit simply tells the program that calls it to terminate and do an exit code of 1, which in C++ is a fail, because if you remember, whenever we have an int main function, we always want to return 0 if it ran successfully. So that's why we're returning is 1. Okay, so here's where the magic really happens. So we have our array, and remember E is our tail. So we're basically taking in the data that they put in and we're putting it into the tail of the array. So for example, if I was to start off here and I was to populate, so I'm gonna just do head and tail and capacity. I really don't like these variable names, but it is what it is. So we added an element. Let's say this element is 6. So we're gonna add that in there. It'll be right here. So our tail is right there. And then a little bit of tricky business. is we're going to increment e by 1, and we're going to modulo it by size. You might be wondering what this modulo size is really there for. Don't worry, this will come up a little bit later, but for now we can just safely ignore this and simply note that we're going to advance e by 1, which is our tail, and then of course our n also moves up by 1. So now our tail, which is our e, will now move here, and our capacity, which was previously 0, is now 1. Cool. Now let's, and remember how the head is still pointing right there. So let's say we do the same thing again and we put in more data. So we want to put in a 0. The same thing happens. We put in a 0, which goes here, and then the e is added by 1. So here you are able to see, okay, this kind of makes sense now. If I was to keep on going, 604, in Vancouver gang, add in a 5, add in a 9. So I'm starting to build a phone number here, but here we've populated our array. And naturally, we know that the first thing to be popped off, the first element that was entered was a 6. So naturally, that's why the head is going to chill here. Okay, so let's go to our peak function now. And like I said, I will go back to this modulo, but a little bit later. So there's a peak, and this peak function has to always check if the array is empty. In this case, it's not, because we've enqueued information into it. However, if you just started the array, you would try to peek off something that wasn't initialized. So that's why we have to do an empty check, and you do the same methodology. See q is empty, and we terminate. And we simply return the element that is f, and remember how f is the same thing as our head. So we simply return what our head is, which would be 6. So if you wanted to dequeue it, and the dequeue will also return the element, but it will also pop it off, so it'll remove it from the array. So what's happening here is we're simply using our front function. Oops. We're using our front function to basically get the value, and then we just advance the head over by 1, and we simply reduce the capacity by 1. So we basically pop this off, we advanced head over by 1, and our capacity goes down by 1. I forgot to update capacity. Before it was 5, but now our capacity is back to 4, and we can also verify that as 1, 2, 3, 4. Okay. Cool. And then, okay, now let's talk about this this modulo size. So, the thing is, like, in our code, we are only doing plus. There will never be a case where e is decremented, and the same thing applies to our head as well. So essentially what's going to happen is that our tail will keep on getting plus, plus, plus. So for example, we are right here, and we know that we have space, which is right here. But since our code is going to do e plus 1, the problem we're going to run into is that our code is going to go out of bounds, and that's really bad. But thankfully, there's a little trick that we can do called modulo arithmetic, which basically will naturally force our tail to go back over here and we can add in more elements into the tail. So how that's done is through the modulo sign. So for a modulo, I'll draw a circle and I'll try to kind of explain what's going on here. So here we have, what mod do we have? So let's say our size is 5, okay? So whenever we do mod size, we're essentially doing mod 5, which is also equal to modulo 5. And how modulo 5 works is, let's break this up into a few chunks. 1, 2, 3, 4, 5. And let's go from here. So the possible values for modulo will always be from 0 to n minus 1, and our 5 is our n. So from 0 to 5 minus 1, which is from 0 to 4. So all the possible values of anything mod 5 will naturally range from 0 to 4. So 0, 1, 2, 3, 4. So if we remember what modulo is simply remainder after division. So for example, if I have 5 divided by 5, well, that's equal to 0. So there's no remainder. If I have 6 divided by 5, well, the remainder will be equal to 1, because there will only be left over once I take out a 5 from 6, so that'll go there. If I have 7 modulo 5, the remainder is then 2, because then if I have a 5 and I minus it from 7, I'm left with a 2. 8 mod 5 will give me 3. Sorry, I should use the modulo sign, not really division. 9 mod 5. Well, if you have 9 points, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and we divide it by 5 points, so 1, 2, 3, 4, 5, if you were to take this and divide it, so that will evenly divide. So these 5 will get taken out, and then we're going to be left with 1, 2, 3, 4 elements left. So that's why 9 gives us 4. And then if you get to 10, well, thankfully, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, these two things can be easily divided into groups of 5. So that will give us a remainder of 0. And we all know that because 10 divided by 5 is equal to 2, and it divides evenly, there's no remainder left over. So, and then the cycle will keep on continuing. So example, 11 divided by 5, we'll go back to 1. 12 divided by 5, we'll go back to 2. So basically, whenever we mod anything by 5, all of the possible answers will always be trapped in this wheel. We'll just keep on doing circles and circles and circles and circles and circles as the numbers grow. And that's beautiful because our number E, which is our head, our tail, will always keep on growing by 1. And so will our head, it will always keep on growing by 1. So this is like 4 mod 5 will leave us with 4. But then if you do 4 plus 1, which is equal to 5, then you do it by size. Well, 5 divided by 5 leaves no remainder. So the tail will go back to here. And then so forth and so on. And then the head will move over and the tail will move over as well. And then if you were to fill it up here, fill it up with an 8, well, our head and our tail will then match to the same thing. However, in this case, we know that our capacity is full, even though head and tail are equal to the same thing. So that's kind of how it works. Yeah, so we need to keep a track of 3 things: the head, the tail, and the current occupied capacity or size of our array. Cool. Okay, let's move on to linked list. So here I have some code that does the same thing, but just with a linked list implementation, and I hope that this makes a bit more sense. So here we have our constructor. Here we have our DQ, which is the same as doing a pop from head, HEAD, our InQ, which is push at the tail, our front, which is a peak at head, and then our is empty. And notice how there is no is full because a linked list doesn't have a fixed size. So as always for linked list, for a singly linked list, in this example, we have our data and our next node. So we have the data and we have our next node, which is simply a pointer to our next node in our linked list, just like that. And we have to keep a track of 2 things. So our head and our tail, which points to nothing. So let's construct our linked list. We're just going to make tail and head equal to absolutely nothing. We're just going to initialize these two to be null pointered. Why? Good question. That is because we just have to initialize these 2 nodes to do something, so we're able to then add to the tail and then modify the head whenever. So this is just simply kind of like temporary. It's just like a placeholder value that will end up modifying later on. So it's just to like make sure like, hey, whatever memory head and tail was allocated to, it doesn't accidentally read that. We're actually just gonna make head and tail equal to null pointer, so we don't accidentally end up reading whatever arbitrary piece of memory head and tail are constructed to. Okay, we have the empty, and the empty is simply gonna check if our head is still null pointer. But why aren't we checking if the tail is null pointer? Well, that I actually don't know, but I think we'll figure it out together. Okay, we have our InQ. So we'll jump back to this. I'm just gonna highlight it in red. And I'm gonna kind of highlight this in red too. Okay. Void Q InQ int x. So if empty, oh, I see. Okay. Okay, I do kind of see what's going on here. 1 second break. Okay, so I'm back. So let's continue talking about the linked list implementation. Okay, so yeah, I mentioned that we check for empty whenever we enqueue something. And if it is empty, we then have to initialize both our head and a tail to be a new null pointer. I mean, a new node, and both of them are gonna point to null pointer. So basically, we start off with our head and tail equaling to null, and then if it is empty, which it is there, we initialize only one node, and it has our data x, and it points to nothing. And this is a trait of it being our tail. But then also, because we only have one node, we'll naturally have this as our head as well. So that's why we also have the head over here. Cool. And then if that's not the case, then simply we basically add new nodes to our tail, but then the head is going to stay here. So what ends up going what what's going to happen is that here we're going to make a new node. So I'll just make a new node right here, and it's going to point to nothing, and we're going to make the current tail, which is this, point to it. So it'll just be like that. And then we are going to make our new current tail the next element. So now we have it just like that. So now we know that this is where we're adding an element, and this is where we're going to pop off. And remember how this was there first, so it will be out first as well. And that's simply what happens in this dequeue. So first we use front, and this is the same thing again to check if it's empty, because we don't want to try to read data from an empty node. And if it's empty, we're just going to exit. If not, then we're simply going to read the header data, which is this X right here, and we're going to return it right here. So I'm jumping ahead. So now we're in the dequeue, and we're going to return it right here, store it as this. And then simply what ends up happening is, now that we are done with this node, we're naturally going to have to delete the node, because remember, a linked list lives in dynamic memory. So we're simply going to back up whatever, we're simply going to make a new node called temp, which is going to be this, right? Because remember how head pointed to here? So we're going to make a new node called temp, which is what we're doing right here. And then we're simply gonna delete this head. And then obviously the next thing to do is to move head to now be the temp. So now we can just make head that temp. And yeah, we just ended up deleting that node. And then let's see, what's this doing? If not head, then tail equals head. Oh, I think this is like an edge case. So this is if we ended up deleting. Yeah, so this is if we only had Yeah, I think this is an edge case where if we had only one node left and we try to pop up this node. So this will make it empty, but basically we would retrieve what's happening here, make a new node called temp, which is whatever head is equal to next, and then we actually end up deleting head, and then we make head equal to temp, and then if head doesn't exist, well then we have to now update our tail, because our tail is now a dangling pointer. It's literally pointing to nothing, so we have to make our tail also equal to this null pointer. And then we just return whatever the value that x was right here. And now we're back to an empty linked list. Yeah, so that's a linked list implementation. Pretty simple, just a high overview. We add to the tail and we pop off at the head. And you guys can just practice and it'll make sense to you. Okay, so this is an example of a singular linked list where the linked list is only broken up in two parts, which is data and then our next. But now let's deal with something called a doubly linked list, which simply, rather than just being data and then next, it also has one more, which is called previous. So now it's kind of like a sandwich in the sense that this is pointing to here, and that's pointing to that, or in another example, so this points to whatever this is, where we have a previous pointing there. You could also draw this as that, and then this as that. So the benefit of having a doubly linked list is that it allows you to traverse the linked list in either direction. So normally, if you had a singular linked list, if you were here, there is no way for you to go back here. So you're kind of stuck. You have to restart all the way from the head and then traverse all over again. However, with a doubly linked list, you are able to easily move forward and backwards as you choose. And that gives us you extra flexibility. Another way to think of it is think of it like a road where you have cars, but a singly linked list, cars can only go in one direction. But with a doubly linked list, you end up having a two-lane road where you can go in either direction, and it is generally a lot more efficient. However, there's more overhead because there's more things you have to deal with, but that's the trade-off you take. So simply put, for a singly linked list versus a doubly linked list, it is simply less to worry about, but also less flexible, and you need recursion to traverse, which I'll talk about a bit more later on. Whereas this one, is more to worry about, but also more flexible and iterative solutions work better or are easier. So with a singly linked list, it's best to use recursion because you naturally get the head back because that's what you want to deal with in a singly linked list. However, with a doubly linked list, you don't necessarily need to use recursion. You can simply use iterative solutions, which involve loops instead of recursion to do its repetition, and that benefits you later on. So it's simply like, do you want something to be simple at first, but harder to navigate, or do you want something that's more difficult at first, but also easier to navigate, and also more flexible, and also faster to navigate? Although the doubly linked list will take up slightly more memory because you have an extra pointer to keep a track of. So it's really up to you. Um, both options are fine. Both options have their pros and cons. One's not necessarily better than the other. It really depends on what use case you want to use it for. But since this is an academic setting, let's just learn about doubly linked lists anyway, so you can make a better informed decision later on if a singly linked list or is more applicable for your specific problem or a doubly linked list is. Okay, so like I said, a doubly linked list has these three parameters, and that's about it. Everything else is kind of the same, except for adding and removing nodes, which is a bit more complicated, but that's a trade-off you get for extra flexibility. Okay, so yeah, so we use the same struct. We just do a previous and a next and a data. And so here's an adder function. I don't know why Professor didn't really um, make a separate class, so we just all did it in one function, so I'll kind of have to break it down. So we have to initialize the node to being equal to nothing, because remember in a linked list, there's always a null. Then here, what we do is, so this right here, so remember how this is our previous, and this is our next, and this is our data. So here, what we're doing is we're basically making h, which is our head, equal to a new node whose previous is null, has a data of 4, probably should make it bigger, which is a data of 4, and then it points to this. So this is also the tail and the head at the same time because there's only one element here. And then we're going to make a new node, and I'm going to do the same thing. Probably should spread it out a bit more and have a new node or should draw better. And its previous is null, its data is 3, and its next points to our next node. So we're slowly building it up. However, a problem that's coming up is our previous is still equal to null, which isn't true anymore because now we've added in this whole node. So now we have to update this previous to point back to this. So right now it's only one way. And to make it two ways, we have to use this where we go, where we're currently, remember, we're always at the head. we're currently here. So now we're going to do head.next. So that moves us right here. And then we access the previous, which is this thing. We access the previous and we point it into the where the head was. Okay, that's kind of a bad explanation, but let me just show you how it works. I'll just try to draw. So this red is going to be me right here, okay? And H is going to still stay. This H is still going to stay where our head is. So we simply are, so remember how this is the next. So this is the previous, and this is the next for all of our nodes, right? So we go here. So we go to our new node, and then we go to the previous, and we make our previous equal to our current H. And that enables us to do this. So now this is now pointing back to our current head. So that's what we're doing here. And we keep on doing it. So as you're building up, you also have to advance over by one and make sure you link the previous node. So let me do one more example here. I'll make a new node. I'll add in the data 2. I'll make it equal to null, the previous equal to null, and then the next equal to this. And now I have to go here and I have to erase the previous and make sure that it points back. So with that, we basically get a doubly linked list, since there's links both ways. Okay. And yeah, the cycle basically continues, and then we just add one more. Also, we aren't talking about queues. This is just a doubly linked list, so no queuing, but like the concept is still essentially the same. It's just that with a doubly linked list, you just have to worry about the extra pointer, the extra previous pointer in each node. And yeah, we just basically build it again. One, and then this points to that. And then we have to go to the next node and make sure it points back. And then, yeah, you basically just print all of this, and it'll print in order. So that's 1, 2, 3, 4. So again, not really a queue. And also, because it's a doubly linked list, we want to stress test, make sure the pointers are linked properly going forwards, and also all of the pointers are linked properly going backwards. So that's why we have a forwards and a backwards. So he's basically saying that this is just telling us it's going to go forwards. It takes an hour ahead, and basically it'll keep on advancing. It will basically keep on going until pdp.next is pointing to a null pointer. So keeps on going until this condition is false, which is when it's all the way at the end when it's pointing to the null. And it's going to keep on doing this on each iteration, which is going to advance to the next node. And then we just print off the data at each node. And then, yeah, I'm not really sure why he put this here, an extra p data print. Maybe it's loop terminated one too early. I'm not really sure. Okay. Anyways, and then we also have a backwards function, and the backwards function instead of doing p.next, now we're going to start, we are going to keep on going until p is also null. So remember how, like, this is also null, right? So we're basically going to keep on going previously until we hit null, and we're just going to keep on printing data. And then this is just to make a new line. And yeah, so that's how the print function works. And then, yeah, uh, quick break. So now we're going to start to focus on adding elements to our doubly linked list. So here's what we had before, but I'm just going to make a simplified version. Oops. So we have a node, it has a previous, it has the data, and it also has a next pointer. And I'm just going to duplicate it. And we're going to call this H. And this can be whatever. It could even be the tail or some other intermediary pointer. I mean, some other intermediary node. And now we're just going to start to add elements. So if we're at the head, our add function over here has an issue where it is going to try to use previous, and it's going to try to read data from our previous later on. So the problem with using the head is because the head, the previous is null, this will cause an error. So we're unfortunately going to have to advance head over to this in order to use the add function. And something called a circular linked list will solve this. But first, let's just show how it's implemented using a normal doubly linked list. So as you may recall, this is how the pointers work. So this is pointing to nothing. And next is just pointing to our node. And then our previous is pointing to our node as well. And then this can be pointing to nothing. So that's kind of how it's working. So for us to add in a new node, we're going to call this add function, and here's the value we're going to add. So here, going here to our add function, first we make a temporary node, and we allocate it in dynamic memory by using the new keyword. And this is our previous, this is our data, and this is our next. So I'm just going to draw out the node here. And also the pointer we're passing in is, the node we're passing in is this one. So we're going to read it. So we're going to add in its previous, which is going to be pointing to this. So we have a previous, a data, and a next. So its previous is going to be pointing to the same thing that this previous is going to be pointing to. So we're copying that previous, right? And then we put in the number we want, which is 42. And then we make the next equal to the node that we're currently dealing with. So we make next, point to that. Cool. So this is what our doubly linked list looks like. And I'm sure you can guess that there's a problem. We have a lot of connections. And if you were to try to print this linked list, what would happen is that we would just simply go here and just follow the next pointer and then go here like this. New node we've made will be entirely ignored, even though the node's own pointers are pointing to the proper things. the pointers for these nodes are not. So that's what we have to fix next. We have to fix this pointer and this pointer. So that's what's happening. So that's what's happening with like these two lines over here. We're just fixing the existing pointers, so when we print out, everything works well smoothly. So what's going to happen is, this may be a bit confusing, but remember that this part will always evaluate first, and then this part will happen. So this is our temp node, right? So we're gonna, and this thing wants a pointer. And we know that wants a pointer because these are like pointers over here, right? So what we're going to do is we're going to take our node, and we're going to make it equal to our current next previous. So that's a bit confusing, but I'll just draw it out. What is our current next? Our current next is this node, and this node has a previous. So we're going to simply make this previous, rather than it pointing to this node over here. We're simply going to make this previous point to that node. And I'll just draw it a bit better. So, whoop, there we go. Cool. So now this side is fixed. Now we have to fix this side. Currently, the issue here is that our head node, or our node over here that came before it, its next is pointing to the tail, so it's going to completely jump our node. So we have to go from our current node, its previous, and its next, and make it equal to our temp. And that's exactly what's happening here. We have our temp, and we're going to its previous, and we're making its next equal to our temp. So what that's going to do is that's going to remove this, and simply make its next point to our node. And now we have established a proper flow. So now whenever we print it out, which is what happens here, it will go from here to there to there, just like how we had wanted it. And then lastly, we have a remove function, and the remove function just essentially undoes what we do. So the first thing we have to do for the remove function is we have to fix these two pointers. We have to fix this one, and we have to fix this one. So that's what our remove does. We basically go to so our P is our current node, right? So our P's, we go to its next, and we change its previous equal to the previous of the node that was passed in. I mean, of our node. So what we do is we go to next. Here, follow along with me. We go to, so I'm just going to follow here. So go to P next, which is here. And then we make its previous, which is this, equal to our node's previous, which points right here. So essentially, what that's going to do is that's going to make a pointer just like that. And then we do the same thing. Same thing for in this one. So we go to back to our P node, which is this one. We go to its previous, so follow along here. And we go here and we make its next. Rather than equaling to our node, we're going to make it equal to our P's next, which is this. So that'll make it look like that. And I know it's getting messy, but now if I remove all the lines, this is essentially what's happened. So we've beautifully removed our node from the pointers. And now we're safe to delete P, and we won't have any dangling pointers. Everything is connected. And that's exactly what happens there. So this method works. However, it is a bit fragile because, as I mentioned, our add function will not work if we're dealing with the head, and our remove function will not work if we're dealing with the tail, because, for example, if you have the tail function and its next is pointing to null, well, we're going to go here, and then we're going to try to access the previous of null, which is going to crash our program. So that's not good. So how can we make our doubly linked list more robust and make these remove and add functions handle both the head and the tail? Well, what we can do is we can introduce something called a dummy node. And the dummy node won't really have any data that we initialize. It will basically just be a gap between the tail and our head. And will also allow us to go both ways. So let me just draw this more explicitly. And I have the code for our dummy node right here. So let's move it over. And let me clean it up a bit. So this is our CDLL. And our homework is to add some memory functions. But I'm not going to do that here. I'm just going to walk you through how it kind of works. And that'll be the end of this video. So in order to initialize our CDLL, we need to initialize the dummy node. So notice that there's no head and there's no tail. The concept of a head and a tail doesn't really exist in a circular linked list. We'll only have like one full trip. So think of it like a group of chains. And then we basically just go through all this data forever and ever. But we know that we are done printing when we arrive back to where we started. And we're going to mark that with our dummy. So that's essentially how it works. So the concept of a head and a tail is completely gone. There is no head or tail when you're dealing with a circular linked list. And the beauty of this thing is that we don't ever have to worry about like accessing, like reaching the end or reaching the beginning and its previous being equal to null and our tails next being equal to null either. So the concept of null pointers goes away when you have a circular linked list, which is nice. And it allows our add and remove function to work beautifully. Otherwise, if you want, our add remove function to work beautifully. Otherwise, you would need to add a lot of like if statements and like edge cases, which aren't fun. Cool. Okay, so we have a dummy node, and our dummy node is basically just a node that has a next and a previous. And it just doesn't really have data. We aren't really going to ever initialize the data. We aren't ever going to read the data. The only function of a dummy node is to tell us where to go next and be able to have a pointer previously. So for illustrative purposes, I will just draw these two, and that'll help us identify our dummy node. And that's basically what we're doing here. We're basically, when we initialize the node, we basically just make a new node, just like this, and it exists in dynamic memory, and we make our dummy previous point to dummy, and our dummies next also point to dummy. So now it's just a node that connects to itself. Here, I'll draw it just like that if you want. Cool. And you notice how there's no nulls, which is really nice. Okay, so now let's try to insert. So for us to insert something, we're basically going to make a node, and its node wait, hold on, let's see. What does this mean? Node P is equal to dummy.next, but dummy.next is currently equal to dummy. Okay, I guess that's hmm. Oh, these two are useful if our circular linked list already has nodes in it. But currently, this doesn't really make sense. So this node will be made. It's a node called, well, actually, no. It's a node pointer called P, and it's currently just going to simply point to our dummy. And the whole point of this P is it's supposed to go around our linked list and try to tell us where we need to insert. But then since we only have dummy, it's basically only going to stay a dummy. And that's what this is supposed to do. This is supposed to advance through the linked list and try to look for a location where we're going to insert the node. So that basically won't really do anything, but for all intents and purposes, we're going to leave it there. So then we're going to make a new node, which is where something's actually made, and it's going to have the value of p previous, x, and p. So let's make a new node. Our previous, our x, and then we have a next. So our previous node is going to point to whatever our p's previous was, which is basically just a dummy. So it's going to point to that. And remember how our p's previous just points to itself. So that's what's going to happen. And then we're going to fill it in with x. And then our next is also just going to point to whatever p was pointing to. So now we've added this. So now we have two nodes in our circular linked list. Cool. But remember how our dummy is still pointing to itself. So we have to fix that. So what we're going to do is we're going to so this node is called temp. So we're going to go to temp.next, which is this, right? Following this arc, we're going to go temp.next and access its previous and make it equal to temp. So now this is going to point to that. And then we're going to go to our temp.previous and its next, which is still the same node, but we go through this way, and we're going to make its next point to our new node. So now we have a circular linked list. And just to clean it up, this is basically what we have. We have a ring. So we'll be able to go here, access this, go to its next, which will go here, go here, go to its next, which will go here, go here, go to its previous, which will go here and its previous and go there, and do all kinds of stuff. We're in a circle. And then if you wanted to add one more, well, so let's say that this is 4, and we're going to add in a 5. So let me show you how that's going to go. So we're going to make a node P. So P is always going to be pointing to whatever dummy.next is. And currently dummy.next points to this node that has a 4 in it. And then we're going to go through our circular linked list for as long as P is not dummy, which currently P is not, and for as long as our number is greater than whatever P data is. And 5 is greater than 4. Let me draw in a different color. 5 is greater than 4, so that checks out. And then we're basically going to make P equal P.next. Let me erase this. And our P.next is going to go back here. And then the whole thing starts again. And we're going to do a check. Is P not equal to dummy? Well, that's false. So now the loop breaks. And now we're going to make a new node. And it has a previous and it has a next. And its data is 5. And we're going to make the previous point to whatever our P's previous was pointing to, which is currently this. So let's draw that out. Cool. Then you have our X, and then our P.next is going to be whatever P is, which is currently the dummy. So we have that. Okay, maybe I should have moved it over here so it kind of makes a bit more sense. So our previous is pointing to that. How can I have to think, how can I draw this in a way that looks nice? Whatever. Okay. You're gonna have to bear with me, sorry guys. So this is gonna go here, and then that is gonna go there. Is there a way to make this look nicer? Yeah, sorry. Okay. So this works, but now we have the same issue that we had before, where if you try to access our nodes, we'll go here and its pointers are pointing here and its pointers are pointing there. So we're completely dodging our new nodes. So what we have to do is now we have to manually change these nodes, these pointers and these pointers to include our new pointer. And that's what happens right here. So we have a temp. So we go to our temps next, which is our dummy. And we make its previous equal to our temp. So now our dummy's previous is going to be pointing towards our temp. Cool. So now one of these is broken. And then we're going to go back to our temp node and make its previous, which is just 4, its next equal to our new node. So this is now going to equal to that. And that will fully break this thing. So if I was to redraw it, I know it's a bit messy. It will actually look like that. And then this P goes away. So now, whenever we print this, I go here, go there, loop around, go here, and then go there and loop around. So that's how we add nodes into our circular linked list. We always start at the dummy. We go through, we see where we want to insert, and then we simply insert by making a new temp node, and we make sure that its neighboring nodes also its previous and our neighboring our next node's previous points to here, and our previous node's next points to here. I know that's a bit confusing. It'll take some time, but I recommend practicing. And then the remove. Okay, let me take a quick break. Okay, so we're going to continue and we're going to focus on the remove function now. So here's the remove function right here. And it's going to search through and look for a number. And then it's going to remove said number. And that's what this if statement basically does. And it's only going to delete if it actually finds it. And notice how it doesn't void anything, so we're free to modify the position of our head, so to speak. Okay, so let's trace it through. So how this works is, so let's just do an example, and let's say, actually, oh wait, this was an insert, this was our P. Wait, did it cover remove already? Seems like I did. Let me just double check. Okay, I didn't cover remove. Okay, so the drawing was actually this one. So this was something else. Okay, so let's walk through it. So if X is found, we're just going to delete the node then. If not, we're just going to continue and not really modify anything. So let's walk through it. So we have our dummy node, right? And also we interface through everything through our dummy node. So that's something important to keep in mind. So we have a node P, and our P is going to go through. Our P is going to be initialized as dummy next. So whatever the next is, so for example, I think this is, yeah, the bottom one's next. So our P is going to be this node right here, that's the 5. And let's say we want to remove the 4, okay? So, and we're going to keep on going through this loop until P is not equal to dummy. So what this is going to do is this is going to remove all instances of the 4. But since we only have 1, we're only going to remove 1. And then we're going to make a temporary node. And it's going to be called P. It'll be whatever P next is. And our next is pointing to this 5. And it's basically is going to do a check like, hey, is our current P data equal to our X? So is 5 equal to 4? And the answer is no. So nothing's going to happen. And then this is going to run. So P is then going to become temp. So our P is now temp. And it's going to do the same thing again. Now temp is then going to become our dummy node. So we're kind of starting to walk in circles here. And it's going to do the same thing. Is our P data, which is 4, equal to 4? And that's true. So now what's going to happen is we're going to unlink everything that's connected to this node and then restore the functionality of the linked list, and then we're going to delete this node once everything's become unlinked. So that's what we're doing here. So we're going to go p.next previous, and we're going to make it to whatever p previous is. So p previous is currently the dummy, and our p.next previous, which is this thing. So basically what's happening is we're going to make this previous equal to back to our dummy. So why don't we do that? So make a link between the previous and the dummy. And then we're going to go to p.next, which is our dummy. And we're going to go to our previous. Oh, I kind of mixed those two up, but yeah, we have to do it for each. So p previous, that's a p previous is dummy, and this thing's next is going to equal to whatever p next is. So here, now we restore the functionality. And then once that's done, we can simply delete p. And then obviously the pointers also get deleted, and our linked list returns like this, and we can cycle around. So basically, the steps to remove and insert are similar. It's just that it's kind of done backwards. So here, so steps to insert is when you do new node, and then you initialize all of the parts of the node, and then you just link the previous node's next to the new node, and then the next node's previous to that node. And then the remove is pretty similar. All you do is you basically link your nodes next. Your nodes previous to your previous is next. So make a link like that. And then you modify your nodes previous is next to your next node. So you get two links just like that. And then you're safe to do a little delete. And then, yeah, everything becomes circular yet again. Also, you have the little dummy in there as well. And you always interface through the dummy, but then with the dummy, you have to do a search you have to do a search through the node. That's the only thing with that dummy. Cool. And then if you wanted to make this into, yeah, I think that's about it. We covered insert. And then, yeah, so for, oh, this is a recursive method. This is an iterative method. Okay, so to print, we basically start with the dummy next, and we call it node p, and we'll keep on going until our p is equal to dummy. And I'm going to keep on iterating through p, printing up p data. That is pretty straightforward. And then let's see the recursive implementation. Wait, these are the same. Oh, no, sorry. This is print in reverse. So we start from the previous, and then we keep on going backwards until we hit the dummy again. So one of them's gonna go clockwise, and one of them's gonna go counterclockwise. Cool. Okay, now let's talk about our queues. So if you remember, a queue just puts a restriction to where you basically add to tail and you remove from head, and you also peak from the head. So let's try to apply it to a circular linked list. So you have a dummy node, and let's say it has these three nodes, okay? And then so our dummy has a previous and a next. It's really up to us what we want to make the front. We could make the previous stuff front or the next stuff front. That's totally up to you. Let's see what we did here. So our front is our next. Okay, so this is then kind of our head, and therefore this was going to go here. Actually, I'll draw this a bit more specifically. So this is our head, and then this is our tail. And we have a front function, and it's basically going to call the empty and basically check if we only have a dummy. That basically where it's next points to itself. That's all. And if not, then we're going to also, I think it should have done an exit here, because otherwise it would yeah, this will not work. Okay, oops. Okay, that aside. So to return the front's pretty easy. We just go to our next and read the data. That's it. That's all that the front does. Pretty easy. It just returns the data. And remember, to enqueue is to add to the tail. So that's why we're starting from the previous, and our next is going to be dummy. And to dequeue is to simply remove the head, and then essentially we're going to make our dummies so basically going to retrieve what our front is, and then we're going to prepare to delete the head. If you wanted to, we could have done something like this, but this is also doing the same thing because you don't have to search for it. So let me walk you through this, and then the video will be over. So we go to the next, and then here we're going to prepare for the deletion of P. So we've already retrieved the data. So now we just have to prepare for deletion. And before we delete, we have to do some tidying up. We have to fix all the links so we can safely delete. So let's do it. So we go to P, next, previous, and then we make that equal to our P's previous. So basically, what this means is like, this is our next, this is our previous. We are going to go to our next, and our next has a previous, and this has a next. And we're going to make this thing's previous equal to our previous over here. So we're going to make a new line that basically goes like this. Cool. So we've taken care of this guy. Now we just have to take care of this guy, or the dummy. So now what we're going to do is we're going to go to P previous, which is our dummy, and make its next equal to our node's next. So I'm going to make this one point to there. Cool. So now we have the ability to safely delete our P and then return the data that we stored. So that's pretty simple. Just safely delete it. And as you can see, the linked list is still circular and nothing's broken. And yeah, that's about it. InQ. We did cover InQ. Okay, so let's just focus on adding to tail now. So we're basically going to make a new node, and we're going to have to insert it. And we're going to make its previous and its next. We're going to make its next point to dummy, and its previous point to that node. And we're going to feed it whatever excess. It doesn't really matter. And then we're going to have to go through, and we're going to have to change this link. So we go to our next, and we modify its previous to point back to us. So we do that. Cool. And then we go to our previous, which is this, and we modify its next to instead point to us. And that's cool. And then this link is then gone. And then now our node is now a part of the circle. And yeah, that's how we enqueue. So yeah, that's about it. I know this was a long video, and I feel like this is probably the most confusing topic that we've covered so far. I find it pretty confusing, even more than recursion. But I hope you found it helpful. And also, our homework, I believe, is to add memory functions. So to make the big three. And I'm sure you all remember what that is. And if not, you can go back to my previous videos and just do some node cleanup. Just doing everything that I've done here. Cool. All right. Take care.